Okay, good morning. Good morning, everyone. I hope you're here. But unfortunately, I can't see the chat. I don't know why. Oh, okay, let us start. Okay, today's topic is complex compounds, complexing and its role in biology and medicine. So as you know, the elements in the middle part of the modern periodic table are called transition metals. Of these, the elements from scandium to zinc occurring in the fourth period, and they are very important because of they able to form the unique nature compounds are known as coordinational compounds. So what are coordinational compounds? They are compounds that contain polyatomic molecules or ions with the coordinational center related to the particles. They can be molecules, can be ions that act to independent existence. Seems hard, but let us try to understand what does it means. So coordination compounds, they should have a coordinational center. Let us check the sulfate ion. What we see here? Sulfur, it's a coordinational center and tetrahedral shape, bonded to the oxygen, covalent bond nature. So what is the problem? It seems like it's supposed to be coordinational compounds, but sulfur plus 6 charged and oxygen charged minus 2, it's not a real charge. It's a hypothetical. It appears if you remember, all electron density completely shift to the sulfur. It's an oxidation state, hypothetical, and that's why oxygen minus 2, sulfur plus 6 charged, we will never ever find as ionic species in a solution. So that's why sulfate ion, it's not a coordination compound. So as a second example, hingidron. It's a molecular complex and is known as a molecular complex, consists two substances able to exist independent, paraquinone and hydroxyquinone. So they are bonded with a hydrogen bond and able to exist independent. The problem is there are no coordinational center. So that's why these compounds, being complex in nature, not coordination compounds. As example of coordination compounds can be taken Tasser salt. It's a copper chloride times 6 ammonia. Seems like it's crystallohydrate, but it's not so. Cobalt plus 3 charged, bonded to the ammonia with the covalent bonds. The nature of the bond I will explain later. So what is here? Polyatomic ion plus 3 charged, in square brackets written. Inside we have cobalt 3 positive and ammonia, each one able to exist independent. So coordinational center, cobalt here, and hybridization of cobalt produces the shape of this complex compound is octahedral. So this is example of coordination compound. The best theory ever explained the structure and properties of coordination compounds was produced by Alfred Werner in 1893. So it postulated a lot of different things. Let us take the most important. So central position metal ion can be atom. In complex is called central metal ion or central metal atom. As there exist some coordination compounds, iron compounds, where iron zero charged. Usually when it's bonded to the carbon monoxide. So what then? Ions or neutral molecules can be both attached to this central metal atom, known as ligands. They are bonded to the central metal atom with their covalent bonds formed due to donor-acceptor mechanism, where ligand is donor of electron pair and the central metal atom is acceptor. This bond is a covalent bond, but because of its presence inside the complex ion, it's known as coordinate bond. Our central metal atom or ion, together with attached to it ligands, known as coordinational sphere or complex ion. They always enclose in square brackets. So this coordinational sphere can be charged, can be not. Due to this, it can be complex ion or coordinational sphere just being neutral. If coordinational sphere, the complex ion is charged, as a molecule supposed to be neutral, outside there's ionic bond way, bonded some or positive or negatively charged ions, neutralizing the charge of coordinational sphere. So these ions or molecules known as ionization sphere or counter ions. Number of them exact to neutralize the coordinational sphere charge. If they are neutral, they are zero charge coordinational sphere, there are no ionization sphere at all. So let us try to understand what is the composition of coordinational compounds. So as I told you just now, it can be coordinational sphere can be charged, can be not. In this case, as you see, it's a -1 charge, it's an ionic part. Coordinational sphere locked in a square brackets outside, neutralizing the charge of coordinational sphere, present counter ion between potassium, which is counter ion or ionization sphere, and coordinational sphere ionic bond. That's why if this compound is soluble, but mostly complex compound, they're quite well soluble in water. So if this salt is soluble, it dissociates completely a strong electrolyte, producing potassium plus and this coordinational sphere complex anion. Inside the coordinational sphere, the central metal atom, if we're talking about mononuclear, that means one central metal atom, so it's written left. It's a rule. So we start with a central metal atom, coordinational center, then it's supposed to be bonded to neutral molecules or ions, negatively charged. There can be found complexes with a positive charge ligands, but they are not mentioned in this topic. So, neutral and negatively charged. Every ligand bonded to the central metal atom, not to each other. Doesn't matter how far they are written from it, from cobalt. Each one with at least one bond. Again, water, ammonia, chloride ion, doesn't matter. All ligands are donor of electron pair. And central metal atom, acceptor. Due to the what is oxidation state of the central metal atom, their number of empty vacant orbitals can be different, and that's why number of ligands can form the covalent bond to it also different. So what is coordinational number? It's a number of bonds, coordinational bonds. Our ligands, or central metal atom, more correct to say, produce with ligands. So number of bonds, not number of ligands. Number of ligands is a ligands number, but they are in ligand inside the structure. There can be more than one coordination site. What's mean coordination site? It's an atom sharing electron pair with a central metal atom. That's mean the donor atom. So can be one, can be more than one. That's why one ligand can be bonded to the central metal atom with at least one bond. Number of ligands and number of bonds are not same, can be higher. Coordinational number can be higher than ligands number. Be attentive. So, according to the number of coordination sites, all ligands can be classified few types. Monodentate, dentus means tooth. Monodentate ligand, it's a one forming one single sigma bond. It's a coordination bonds. One single sigma bonds by donating only one electron pair to metal atom. As example, here we can mention neutral molecules like ammonia, like water, like carbon monoxide, which donate only one electron pair. In ammonia, nitrogen is coordination site, donate one electron pair. Oxygen in water and oxygen in carbon monoxide. And also negative one charged ions, anions, they also donate one electron pair. Chloride, bromide, nitrite, nitrate, and so on. Negative one, cyanide, one of them very stable complex. So these ions formed one bond each. That's why in this case number of ligands and number of bonds are equal to each other. Let us see how the structure of complex compound looks, how it looks like if there are only monodentate ligands in. So this complex, as you see, without any counter ions, our coordinational sphere zero charged. What is here? Cobalt plus 3 charged, bonded to the water, 2 ammonias and 3 chloride ions. Let us try to determine coordinational number of cobalt. Every ligand mentioned here is a monodentate, as donating only one lone pair. So every ligand, one bond. Number of ligands, 6. That's why coordinational number of cobalt 3 positive here equal to 6. Please be attentive. Oxidation number and coordinational number definitely not same. Oxidation state, oxidation number of cobalt is 3 positive, it's a charge. And coordinational number, it's a number of bonds. So that's why schematically we can say that this complex compound looks so. Cobalt 3 positive bonded to each ligand as they are monodentate. Here we will get not the perfect octahedral, but it's close to be octahedral structure. So, Dex nature ligands, bidentate ligands, bi means 2. Ligands contains 2 coordination sites. That means able to form 2 sigma bonds with the central metal atom. There are few examples of bidentate ligand. A neutral can be, only one you should know, it's ethylene diamine, organic compound. It's definitely not an IUPAC name, it's a common name. So ethane diamine, it's a IUPAC name. Ethylene diamine, it's everyone should know. This is the name of this ligand when we deal with biochemically important substances. For shorter, to not write such long formula, inside square bracket usually we indicate EN, means ethylene diamine. Take a look, 2 nitrogens from amino groups, they are donate electron pair. That's why this one ligand can form 2 sigma bond, and it is. Also, as it's supposed to be clear, if the charge of anion -2, it can form, in theory, can form 2 sigma bonds with a central metal atom. So what here we can see? Oxalate ion and thiosulfate ion, they are both -2 charged, and they are both oxygen donate electron pair, and that's why they are bidentate always, forming quite stable ring structure with a central metal atom. Carbonate sulfate, they can be bidentate but also can be monodentate if not enough space inside coordinational sphere. But oxalate and thiosulfate almost always. So let us see how bidentate ligand forming the bond with central metal atom, and as example ethylene diamine. So this complex cation, as you see, coordinational sphere is +3 charged, cobalt 3 positive, and neutral ethylene diamine. ligand number here equal to 3. But let us see what is coordinational number. As each ligand is bidentate, each one 2 times 3, that means there are 6 bonds, cobalt coordination bonds to our ethylene diamine. So that's why ligands number equal to 3, but coordinational number equal to 6. As you see, in such case, if they are bidentate ligand, so each ligand forming ring structure, where central metal atom is a part of the ring. So such complex compounds much more stable as complex compounds with a bidentate. It's not a law, can be, but much more stable. So, and the third type, if there are 3 and more sigma bonds with a central metal atom, such ligands are known as polydentate. Triethyl hexa, usually not more than 6. So polydentate ligands donates 3 and more electron pairs. As example, you should know just one. It's EDTA, ethylene diamine tetraacetate ion, which is 6 hexadentate. That means forming 6 bonds each. Let us see how this structure looks like. So ethylene diamine tetraacetate ion, EDTA, it's a hexadentate. That means ligands number equal to 1, but coordinational number equal to 6. Complex compound I will not show you, but the ligand nature is ethylene diamine tetraacetate, 4 oxygen coordinational sites and 2 nitrogen. So total number 6. It seems like this ligand kept as an octopus. It catch the central metal atom and 1 forming 6 bond. It's a unique structure, and that's why we use EDTA salts as antidotes against heavy metals, toxic elements. It's formed much more stable bonds, much more stable structure with a heavy metal than these heavy metals forms with our proteins in our body. So now let us see how can we classify complex compounds themselves. The previous classification was a classification of ligands. So complex compounds, according to the charge of complex ions, can be classified into 4 groups. First one, neutral complex compounds, if coordinational sphere not charged at all. So what we see here, 0 charged complex coordinational sphere complex ion, that means no counter ions, and that's why no ionic bond there at all. Only coordinate bond present between central metal atom and ligands. That's why these compounds, neutral compound, they are very, very, very weak electrolytes, weaker than water even. That's why in some books they are mentioned even as non-electrolytes. Cationic complexes, coordinational sphere is positively charged and neutralized by counter ions anionic nature. Anionic complexes, coordinational sphere is negatively charged, and here one of the most famous potassium hexacyanoferrate complex compound. So here potassium, it's a counter ion neutralizing the charge, negative charge of coordinational sphere, and can be case where cation and anion both coordinational spheres neutralizing each other. Such complex compounds are known as cationic anionic complexes with a dash, cationic dash anionic, and the bond between coordinational spheres is ionic bond. So, but inside each one they are coordinate bond. There are different ways to name such compounds. Second classification of complex compounds according to the nature of ligands. If ligands are same nature, I mean same molecule or same ions, such ligands and such complex compounds are known as homoliganted. And if they are ligands different molecules or ions, heteroliganted. So homoligand, due to what is a ligand there, can be classified at a few types. For example, aqua complexes, they are water as a ligand only. Amine complexes, ammonia. This one of the complex was described with Alfred Werner. Hydroxyl complexes, proving that aluminum hydroxide is an amphoteric compound. Can be acido complexes if their ligand is any acid anion. Cyano complexes, nitrate, sulfate, oxalate, or any anion of acid. Carbonyl complexes are quite unique structure. One of the carbonyl complex everyone knows, a complex of carbon monoxide with a hemoglobin. So here example, it's a carbonyl complex with iron, where iron is zero charged. It's a quite unique structure. Binuclear complex. And from biochemical and medical important complex compound, it's a complex compound with organic ligands, which can be amino acids, like in here in example, our proteins, huge number of enzymes. All enzymes are proteins in nature, and huge number of them, they are complexes of proteins with metal ions. So it can be metal complexes or proteins, for example, our hemoglobin. The examples of such complex compounds. And the last classification of the complex compounds is classification according to the formation of cycles, includes our central metal atom. If there are no cycles at all, such complex compounds known as non-cyclic. So all ligands are supposed to be monodentate. If at least one bidentate or polydentate ligand present, such complex compound is known as chelates. From chela means claw. So these complex compounds have enduring structure between a ligand and metal ion. For example, complex compound of cobalt with ethylene diamine. As you see, ring structure includes our central metal atom in. It's important because of some ligands like pyridine, benzene, they can be as a ligands but monodentate. They're forming one single bond with a central metal atom. Here we have two at least. So, and now before to discuss stability and other properties of complex compounds, let us see how to name properly. And here are a lot of different possible ways to name, but we're interested in IUPAC international system. In any country, we will understand each other. So, same as a salts names, we should follow some rules, some steps even, we can say. So first of all, doesn't matter what complex compound or its ordinary salt. The name of complex starts from the positive ion part, and then we name negative. So neutral we have only one name. So positive ion, cation we name first, followed by anions. When we name the complex itself, and doesn't matter is it a complex ion, cationic place or anionic place in a coordination compound, we name ligands first and then only central metal atom. When we name ligands, and here please be attentive, anionic ligands we name first. If there are few different ligands, anionic nature, we use alphabetical order. Then, after anionic ligands are named alphabetical order, we name neutral ligands. If there are few of them in alphabetical order, please be attentive. Alphabetical order, it's not for all ligands, but for each type of anionic, negatively charged alphabetical order, then neutral alphabetical order. For when we name anionic ligands, negatively charged, they should be with a suffix O. New suffix appears. So that's why here not bromide but bromo, fluoro, chloro, bromo, hydroxo if we deal with OH. It's not hydroxide now. when we deal with the ligands. That means inside square bracket. Outside, as the ionization sphere, they will have same name as for normal salts, but as a ligand they have suffix O. For NO2 minus, there can be two possible cases due to what is coordination site. If it's nitrogen, it has name nitro. If oxygen, nitrito, from nitrous acid. Usually when it's nitrito, we even write this ligand ONO. 2 minus charged as well as 3 minus charged also can be ligands, and that's why they have suffix O finally when we name it. So carbonato, sulfato, oxalato, phosphato if they are phosphoric acid anion, acetato if acetic acid anion, nitrite or nitrato due to is it nitric acid or nitrous acid, and cyano, as I told you, one of the most strong bonded ligand. Neutral ligands, they are used in the same name as their normal molecule name. So if it was pyridine, it's pyridine. Acetyldiamine is acetyldiamine, but there are 4 common exceptions. Ammonia, we never call ammonia, it becomes amine. Double M, please, because of acetyldiamine, where amino group, it's a 1M there. Water becomes aqua. Carbon monoxide, carbonyl, and nitrogen monoxide, nitrosyl. If there are few same type of ligands, with few water molecules, few ammonia, few chloride ions, there we use prefixes, Greek prefixes, dia, tri, tetra, penta, hexa. Usually coordinational number not more than 6, but they are found some complex compound with more than 6 bonds. So dia, tri, tetra. But if their ligand is polydentate, not bidentate, please, polydentate, 3 and more bonds, or inside the ligand name already present Greek prefix, diatria, or other numbers like acetyldiamine. So there are the list of prefixes is used, bis, tris, tetrakis. So after ligands are named, again negatively charged alphabetical order first with the prefixes dia, tri, tetra, and so on, if they are few same. Then neutral named, they are normal names of the molecules, but 4 common exception also if there are few different alphabetical order, and with the prefixes indicates number of them if they are same nature. Then we're ready to name central metal atom. And here classification according to the charge of coordinational sphere we must use to name properly. If complex is cationic or neutral, the metal is named same as the element, English name of the metal. So for example, cobalt is cobalt, gold is gold, silver is silver, iron is iron. Ferrum it's not English, ferrum it's a Latin. So that's why if they are Fe, we name it iron. But if complex is anionic, please, it has new suffix, it ends with the suffix ate. Same as the sulfate, carbonate, anionic place. And there we should use Latin name of the metal. Cobalt, Latin English, same, that's why cobaltate. Platinum, platinate, but some metals, like iron in English, becomes ferrate in anionic. Copper, when we deal with a cationic or neutral, become cuprate, cuprate when we deal with anionic. Lead, plumbate, silver, arginate, gold, aurate, tin, stannate. After the name of the central metal atom, we must indicate the oxidation state of it using Roman numeral, definitely in brackets. Such number is known as Stokes number. And usually, as you know, even when we name any salt where central metal atom can be in different oxidation state, this Roman numeral must be mentioned. And now let us practice. First one, complex compound, cationic nature as you see. Let us name it. First thing we should do, we should indicate all charges there. It's a real charges here, not oxidation states, just it's a real because of every and each part of this complex compound can and it is exist independent. So definitely we should start with the ionization sphere. Here nitrate ion, we have 3 of them, each one -1 charged. That's why we understand that coordinational sphere is +3 charged. Inside there are only neutral ligands, 0 charged each, and that's why cobalt is +3 charged. So let us name. The procedure of naming, we need to name cationic part first. It's a complex ion name. And then ligand, coordinational sphere, ionization sphere, sorry. So ligands, they are neutral, and that's why we name them alphabetical order. Tetraamine diaqua. Alphabetical order, amine first, aqua second. Tetra and di, it's not a part of the name, it's just a prefix. Tetraamine diaqua, then cobalt. Roman numeral means oxidation state of it, and the second word, it's an ion name, nitrate. Cobalt nitrate sounds as a normal salt. That means our suffixes, we can be sure, are correct. Tetraamine diaqua, cobalt, Roman number 3, oxidation state of cobalt, and second word nitrate. We shouldn't indicate 3. It's not trianitrate. According to IUPAC system, we indicate the oxidation state of the metal, and it's enough. So coordinational number, if we're interested in, we can see that here all ligands are monodentate, and that's why coordinational number of cobalt equal to 4 or equal to 6. Second example, also cationic, if there we have 2 different ligands, negatively charged and neutral nature. So again, the first step, we should indicate the oxidation states. Starts with the ionization sphere, which is bromide, and it's -1 charged. 2 of them, that's why coordinational sphere is cation with a +2 charged. Chloride -1, ammonia neutral, that's why platinum reached +4. So now, not alphabetical order, but we should name negatively charged ligands first. So that's why diachloro, suffix O for negative charge, doesn't matter is it -1, -2, -3, diachloro and tetraamine. Then we name English name central metal atom, platinum, 6, here charge +4, that's been 4, bromide. Now the neutral. There are no ionization sphere at all, that's why there will be one but lone name. Again, same step, we indicate the charge. And now we can see the order of naming. Negatively charged ligand we need to name first with the suffix O, dianitrato. Then we need to name neutral, but this is lindiamine, consists dia already in a structure, that's why prefix bis. Then the lone name ethylenediamine we should lock in the brackets to separate this name from previous and further coming. Then we name our central metal atom with the English name of the element. It's a one word. Here supposed to be no dash between, no distance between. It's a one word. Seems like ligand's name are prefixes for cobalt. It's a cobalt, but cobalt with such substances bonded to it. Roman number 2, it's a charge, must be mentioned then. Here, if we're interested in coordinational number, we will see cobalt +2, here 6. Untypical, usually cobalt +3 is, but as example, let us use this. Now, anionic. So, same step, we need to indicate all charges. What we see? Potassium is ionization sphere, it's outside, and our complex ion -3 charged. Here we have negatively charged, 2 of them, that's why we need to name them alphabetical order, then 1 neutral, and iron +2 charged, we should name the last. So potassium, it's a first word. Now we should name the lone our complex ion. Bromo, alphabetical order first. Then tetra, cyano. Suffix O for both, and they are negatively charged. Then aqua, it's a name of our neutral ligand. And then supposed to be as it anionic, not English name of the element, but Latin with a suffix ate. This is ferrate. Roman number 2, the oxidation state of the central metal atom. Potassium bromotetracyan of aqua ferrate. So after we practice with the cationic and anionic, now let's combine naming cationic dash anionic. So here cation we should name first, followed by anion. The first step same, we should indicate charges. Here cation should neutralize anion, that's why we know what is the charges of our complex ions here. So and now two long words. First one to name complex cation, it's a tetraamine copper, English name of the central metal atom, Roman number 2. And second word, tetrabromopaladate 2, copper paladate. This is the complex compound name. Each one complex ion, inside each one there are ligands bonded to the central metal atom. That's why each element here, copper and palladium, each one has own number of bonds, even if they looks same. No, here copper plus 2, coordinational number of it equal to 4, and palladium plus 2 equal to 4. They are independent. So doesn't matter what is a central metal atom nature. It's important, definitely. Some central metal atoms forming more stronger, more stable complex compounds, but ligands nature also important. Number of coordination site also important. Some coordination bonds here more or less stable inside the complex compound. That's why stability of complex compound is different. So how to understand how stable the complex compound? First of all, let us understand stability of complex. What dissociation depends on. So here, in such complex compound, as you see cationic nature, there are present ionic bond between chloride ion and complex ion. That's why between chloride and complex ion, this ionic bond can be, and it is destroyed due to dissociation, strong electrolyte dissociation. So here interionic interactions backward present, but when we deal with dissociation of strong electrolyte, we know it's 100% happen, and we can ignore formation of ionic pairs for now. So first step, it's a strong electrolyte. That's why dissociate completely in the complex ion plus 3 charged and 3 chloride ions. That's why even test reactions can help us to understand that there are a lot of chloride ions and this complex ion present there. But inside complex ion, there are covalent bond, quite strong one, between cobalt and ligands. That's why second step, as a weak electrolyte, this complex ion also can dissociate, but very, very poor as a weak electrolyte. As I told you, for some neutral, we can even say that it's a weaker electrolyte than water itself, almost non-electrolyte. So it dissociates definitely not completely. It's a small part of it dissociate into ions. That's why a huge number of complex ions stay to be not dissociated. So every component of this complex compound released free, but definitely not completely. Cobalt plus 3 and 6 ammonia. This dissociation not happens step by step, it just happens little, but not step by step. So equilibrium reached. That's why equilibrium constant we can use here to describe how well this complex compound dissociate. This equilibrium constant, it's same Kc as we discussed for solutions, so known here as instability constant, because of as higher this value, as more ions and molecules produced due to dissociation, as less stability of this complex ion. As you remember, I hope, instability constant as well as equilibrium constant is a mathematical product of concentration of products in power of balance over mathematical product of concentration of reactants in power of balance. Here only one reactant, it's complex ion. That's why here we have two square brackets. They are different meaning. The inter one, it's a part of the structure, means that this is complex ion. Outside one means that mole per liter, it's a concentration of this complex ion. The opposite value of instability constant is known as stability constant. It's a 1 over instability. That means as higher the instability, as lower the stability. The smaller the instability, as greater the stability of the complex ion. For coordinational compounds, as well as for other salts, as well as for some organic compounds we know, the isomerism is possible. Here unique nature isomerism can be, it's isomerism typical only for coordination compounds. So here can be structural and stereo, structural isomerism, ionization isomerism, hydrate and linkage or bond isomerism. And stereo isomerism, there are two types, geometrical or geometrical isomerism and optical. Optical, as you know, it's diastereoisomerism, more correct to say. Okay, let us see how this isomers looks like. And let us start with ionization isomerism. So ionization isomerism means that general formula of the salt is same, but there are different arrangement between coordinational and ionizational sphere. So as you see, Bruta formula is same, number of molecules and ions is same, but in first one, sulfate is ionization sphere. In second, sulfate is a ligand. That's why due to dissociation as a strong electrolyte, first one compound produces huge, big amount of sulfate ion. That's why I give us set of reaction to identify presence of sulfate. For example, reaction with the barium 2 positive producing a white colored precipitate of barium sulfate. And here the second one produces bromide ion as a strong electrolyte. That's why reaction with the silver nitrate produces white yellow colored silver bromide salt. And even initial solutions of this complex compound, they are different colored. Usually complex compound, they are quite intensive colored. For example, the first one here, violet, intensive violet, transparent solution, as well as second is red colored. Linkage isomerism appears because of different coordination site inside the ligand. So nitro and nitrito. As I told you, if their coordination site is nitrogen, this is nitro complex, and here we can see it's a yellow colored. If their oxygen is a coordination site, it's a monodentate as well. But the complex compound even different color. They have different nature, stability, they have different physical property, even color proves this. Next type of isomerism is hydrate isomerism. Because of water can be ligand, being covalent bonded to the central metal atom, and can be present as a crystallohydrate, which is attached to the whole molecule of our complex compound. So this is hydrate isomerism. In first one, as you see, water just a ligand. It's a violet, and that's why water present due to dissociation in very amount. And it will be present in instability constant as well. Here just 5 molecules of water as ligands present, and outside it's a 1 molecule as hydrate. It's a light green color. Optical isomerism I will not show you here, but you should understand if they are all ligands, 6 ligands are different nature, or 4 ligands are different nature ligands, they're possible to get optical isomers because of there will be chiral center. So geometrical or geometrical isomerism means there can be cis or trans isomerism, but it's happened only in a case they are square planar structure. Because of complexes, they have different geometry. Can be octahedral, can be square planar, not so often can be tetrahedral shape, can be bipyramid, and so on. So geometrical isomerism appears if the plate present, DsP2 hybridization, and the different arrangement of ligands above and below this plate. If they are same ligands, same side of the plate, both below and other both above, this is cis isomer, and if they are different arrangement, they are trans isomers. Trans isomer of this compound, it's a diachlorodiamine platinum. This compound not used in medicine, but cisplatin, it's a cis isomer we use as anti-cancer drug. We can't even explain how important complex compound in biology and medicine. So as example, I will give you just few, the most famous complex compound with organic ligand, porphyrin. So it's a complex compound, it's organic ligand, tetradentate, that's why one ligand forming 4 bonds with a central metal atom. And an example of such compounds consist such type of ligand is chlorophyll, hemoglobin, and vitamin B12. They look similar, but they are different central metal atoms. In chlorophyll, they are magnesium. It's a green pigment, as you know, plant pigment. Hemoglobin, they are iron 2 positive as a central metal atom bonded. Hemoglobin, it's a chromoprotein, red pigment. And vitamin B12, they are cobalt central metal atom. It's essential vitamin deficiency. It's participate in the formation of blood, and not only. And deficiency of this vitamin cause cancer type of anemia. So structure of heme, it's a structural component of hemoglobin. As you know, I hope you saw how hemoglobin look like. There are 4 subunits. In each one, protein bonded to the heme. It's a chromoprotein. And the heme looks like I just told you. So porphyrin, 4 bonds with the central metal atom, which is iron 2 positive. It's carry oxygen, you know. And vitamin B12 looks much harder. Cobalt here as well as in hemoglobin, the 6 coordinational number equal to 6, but to porphyrin just 4. Other 2 other substances, other 2. So here cobalt is essential. Also, as I mentioned, some organic substances can be used as antidotes. And here chelatotherapy we can explain using such structures as unitiol and complexons. Unitiol, it's a sulfur-containing organic compound, which is quite useful against poisoning of some heavy metal like mercury, cadmium, lead, chromium, and cobalt. And complexon, they are derivatives of ethylene diamine tetraacetate, or just itself, known as trilone A. Sodium salt of it, it's trilone B, and tetracene, they are mixed salt, calcium and sodium. Very good, and very good as antidotes. Why? Because of this compound itself, trilone A, trilone B, and tetracene, they are non-toxic themselves. They are formed as their 6-membered, 6 coordination site. They're forming very stable complex compounds with central metal atoms, and much more stable than our proteins forming this with these heavy metals. And the result of complex, the resulting complex with trilone A, B, or tetracene, they are not toxic and can be excreted easily through using kidneys. Kidneys will be not damaged. So that's why these antidotes are quite useful and easy to use. No, this is it. If you have any questions to ask me now. Алло, Дим, у меня вообще непонятно, что он ушел. Я не знаю, я не вижу чата. Я сейчас читаю, остановить не могу, у меня не загорается восстановить презентацию. Я вот сейчас сижу, говорю, у меня лекция, я вообще не знаю, она у меня записывалась или нет. Были дети или нет? Ну, хорошо, давай. Okay. So, if there are any questions? No questions. No, ma'am. So I want to remind you that you can't be late. So that's why, as I see, there are some students join to us after a lot of. Some were present just within 13 minutes. The lecture, 1 hour lecture, can be 1 hour and a half due to information and questions you want to ask. So that's why it's unacceptable situation. What has happened here? 8 o'clock, 5 minutes before 8, and any other lecture you already. Now I'm talking to you not as a teacher, but as a vice dean who form in the group. You know, every single day we discuss with you the problem appears. Every single day. So that's why it's essential to be in time. As I told you, it's a disrespect to teacher. When you're late, it's necessary to on your computer and join. And I know that there are a lot of, there are 2 hour and a half time difference. It's for us, it's a very early morning. For you, it's almost afternoon. And to be late, it's an unacceptable situation. So if it will be going, if I will see that you're late practical class and lecture, as a vice dean, I will inform your parents. Because of this means they should wake you up in time. You represent your country right now here. You represent your family. And if you are unable to organize your time sitting in your room, at home, that means you can't study online. So you should now understand you are in higher school and doesn't matter, you're in India. You here, it's online education. It's not a distant just to get task and do whatever you want. Class time, you must be in contact with the teacher. This is online education. Kesharisha asked something about spaces while writing your back name. Space between complex ion name and counter ion name. Same as when we name like sodium chloride. Sodium first word, chloride second. They are not together. They are distant between them. Iron, chloride. But when we name complex ion like diachloro, tetra, aqua, platina, this is one word, then Roman numeral for platinum charge, and then distant, one symbol distant to the anion name like chloride, outside one. Okay, so if it's there are no more questions, lecture is over. You have 2 more lectures. One is 9:50. You have time now to rest. And please don't be late. I don't want to feel shame that you are. I'm the one who organized you. I'm the vice dean. Нажал. Okay, so goodbye. Lecture is over. У меня не открывалась вот эта страница.
Я, короче, сказал.
Это сейчас... Я